So 3 dots. So what do you see as my name?
Host 500.
Okay. So I go through the 3 dots.
I could manually change it also if you're on mobile and you're having a hard time finding.
Yeah,
it.
I'm not
Yeah,
getting.
if you
I'm
could
not
do
getting
that.
it when you do the 3 dots. If you right click on your picture. But if you're not on your computer, you can't right click.
But maybe Nick can support you there.
Yeah, give me just 1 second. I should be able to just override it.
Great. But then it seems like you have
There we
everything
go.
under control.
Yep.
Perfect.
Yeah,
Okay,
I think we're
perfect,
good to go. This one, they made it easy for me.
Yeah,
Thank you all.
great, Nick. Great. Then I'm gonna log out.
Hello, and thank you for joining us. My name is Jeff Montera, and I'll be moderating this session. I'm the director of CDM Smith International Development Practice, where we partner with clients across the globe on designing and implementing sustainable infrastructure that accounts for the rapidly increasing challenges posed by climate change. Today, we'll examine solutions to the problem of decreasing freshwater resources in a changing climate. Before we begin our session, let's learn a little bit more about each other. While we briefly introduce you to our environmental engineering firm and speakers, please drop your primary areas of focus or water challenges in the chat feature on the World Water Week website. First, a bit about our organization. CDM Smith is a global, privately owned engineering and construction firm that was founded in 1947 and is proud to provide legendary client service and smart solutions in water, environment, transportation, energy, and facilities. Ranked number 4 in water by Engineering News Record, we are eager and able to lead solutioning in the water sector that addresses the critical issues being discussed at World Water Week. I'm pleased to introduce you to some of CDM Smith's best and brightest and share our session's agenda. In part 1, we examine new tools and techniques for identifying and quantifying the quantity and quality of groundwater resources. We'll hear from John Doherty, who will speak about the engineering practice of exploiting oil and gas exploration data for groundwater development. Then we'll hear from Henning Moe, who will share a CDM Smith case study on the potential for exploitation and challenges of brackish water development in Jordan. And then Philip Schuler, who will talk about an exciting new approach to quantifying the susceptibility of groundwater to drought with a case study from Ireland. In part 2, where we focus on implementation solutions for the freshwater supply crisis, we will hear from Greg Wetterau, who will speak about the expanding practice of groundwater desalination in the United States. And finally, Jose Maria Guzman, who will share a case study of the Chilean mining industry's use of seawater desalination as an adaptation measure. We'll take a single question after each speaker's segment and open up a Q&A session at the end of each part. Please use the Pathable Platform poll feature to submit any questions, not the chat, and include your email address so we can follow up with you if we're not able to get to your question during this session. Before we get into the solutions, let's take a big picture look at the problem. According to IPCC's 6th assessment report entitled Climate Change 2022, Impacts, Adaptation, and Vulnerability, groundwater abstraction is projected to deplete long-term, non-renewable storage as withdrawals are projected to increase significantly in all major aquifers worldwide. In addition, climate change is expected to negatively impact groundwater quality. First, with increased precipitation intensity and storms leading to both chemical and organic contamination. And second, a projected rise in sea levels leading to saline intrusion. From drinking water to agriculture to industry, we rely on groundwater resources. It's critical that we begin to prepare for these projections. Today, we'll share case studies that demonstrate new tools and techniques for identifying quantity and quality of groundwater resources as well as solutions for utilizing these stress resources. With that, I'll hand things over to John Doherty.
Thank you, Jeff. Hello, my name is John Doherty, and I'm a hydrogeologist with CDM Smith based in the United States. Today, I'm going to present a case study about a project in Tanzania which bridged the gap between oil and water sectors, and where oil and gas exploration data were recycled to identify and characterize the deep Kimbiji aquifer south of the city of Dar es Salaam. Dar es Salaam is located on the Indian Ocean in Tanzania on the east coast of Africa. Dar es Salaam is the economic and diplomatic capital of Tanzania. It's the second largest port in East Africa, with an annual population growth of about 6%. It's projected to be a megacity with a population greater than 10 million by the year 2030. The aquifer I'm going to talk about is called the Kimbiji aquifer because it underlies the Kimbiji Peninsula, which extends along the coast south of Dar es Salaam and inland. In Dar es Salaam and around the world, conventional freshwater resources, groundwater resources, are being depleted and polluted. These aquifers are generally a few tens to perhaps hundreds of meters deep, but the extent of freshwater or brackish water aquifers deeper than 400 meters is still largely unknown. This case study from Tanzania illustrates the first time oil and gas data were recycled to identify a deep aquifer, one, in other words, greater than 400 meters deep. New discoveries of deep aquifers depend on being able to see deep, and oil and gas industry data contribute greatly because their data typically extends below 400 meters. Here's an example of a log from an exploratory oil and gas boring completed near Dar es Salaam. Near Dar es Salaam and offshore, oil and gas exploration activities from the 1980s included the collection of seismic profiles and drilling of oil and gas wells. Rudin and CDM Smith also completed resistivity profiles. Our partner in this project, Rudin, recycled this oil and gas data and used a machine learning algorithm to work with the data. Here's an example of a seismic profile on the top of the slide, where he used this to identify the Neogene period sediment, which defined the Kimbiji aquifer and the aquifer boundary, and to develop the geologic model shown in the bottom half of the slide. The Kimbiji aquifer is in the Neogene period deposits. The oil and gas data allowed us to see and define the vertical extent of the sedimentary package, which is up to 1.5 kilometers thick offshore. These data were used to identify a series of faults, to estimate the elevation and the thickness of the Miocene epoch deposits. Rudin published this work in 2007. This deep coastal aquifer extends over an area of approximately 2,500 square meters and ranges in thickness from 200 meters to approximately 1,500 meters. CDM Smith worked with Rudin to develop a project which was funded by the government of Norway. The project included the drilling of 7 exploratory wells, completion of an aquifer development plan, completion of a strategic environmental assessment, and a preliminary design for the preferred alternative. The project started in 2011 and concluded in 2017. The exploratory borings I'm going to show you were completed to a depth of 600 meters using reverse circulation drilling mud method. And that depth was just a limitation of the drilling equipment available, which points again to the importance of the oil and gas data to see below those depths. The borings were completed in 3 stages. Stage 1 consisted of the installation of the surface casing. Stage 2 consisted first of advancing a pilot hole to about 200 meters, after which a suite of borehole geophysical logs were run. The borehole was then over-drilled and a 24-inch pump house casing was installed. And during stage 3, the pilot hole was advanced to about 600 meters and the suite of borehole geophysical logs was run again. The borehole was then overdrilled for installation of the well casing and screen. Now, before the well casing and screen were installed, the suite of geophysical logs, including natural gamma on the left and a velocity log on the right, were reviewed, and the aquifer, which consists of thin beds of sand and gravel interbedded with clay and marl, was identified. CDM Smith developed a groundwater flow model based on the geologic model developed from the recycled oil and gas data analyzed by Rudin and from the data generated by the exploratory boring program and previously drilled wells. The model included the Combiji Peninsula and the offshore area where oil and gas data showed that the aquifer extended. This cross-section is drawn from the southwest to the northeast and shows that the model extends 3,500 meters vertically and more than 100 kilometers horizontally, and includes data from the exploratory borings and, again, the oil and gas wells. We used this model to investigate how far offshore freshwater extended and where the seawater freshwater interface is likely to be, both currently and historically, factoring in sea level change over the last 30,000 years. The red line indicates the current position, and the blue line indicates the historical position. The modeling showed that even under conservative assumptions, freshwater extends at least 20 kilometers offshore in the aquifer. We then used the model to evaluate things like water table drawdown under different well placement and pumping scenarios. This pumping scenario was at 250,000 cubic meters per day for a period of 100 years, which gives you a sense of the capacity of this aquifer. The work was then used to support the aquifer development plan and strategic environmental assessment. In closing, this project bridged the oil and water sectors and recycled data to successfully discover a deep freshwater aquifer and then to evaluate it for future development. Thank you for your attention, and I'll be happy to answer any questions.
Thank you, John. One question here. How do you get access to the oil and gas data for a project area?
Yeah, that is challenging. It depends on the location that you're in. You start with the, I'll call it the state authority, not necessarily the national authority, but it would include national authorities as well, because often oil and gas industries submit some of that information to those bodies. And then, of course, you can reach out directly to those organizations, talk to people in academia who are working in the oil and gas field, and in that way try to get access to the information.
Okay, great. Thank you again. Let's turn it over to Henning Mo to talk about using brackish water in Jordan. Henning?
Well, thank you very much. My name is Henning Mo. I'm also a hydrogeologist. I am currently sitting in a very wet and windy west of Ireland. But I am going to be speaking about the opportunity and the challenges of brackish water development in Jordan, brackish groundwater in particular. Next slide. And so the context, much like Combiji, is deep groundwater. In this case, it's brackish groundwater. And before I proceed, just to recognize that deep groundwater is used, exploited in many countries, but new and exciting discoveries are also being made, partly on the back of use of oil and gas data. And I just wanted to reference two particular and interesting projects in Africa. One on a passive margin geological setting in Somalia. And there's a recent article in the Journal of Hydrology written by Quiroga et al. And at the end of our session slides, you will find the full references for this, and it's good reading. The second example would be the in structural and sedimentary basins, and there's a very good case study in emerging in Namibia, border of Namibia and Angola, by the German group BGR, along with the Geological Survey of Namibia. And there's a paper reference at the end of this session by Huben et al., written in 2020, which is also very good reading. So back to Jordan. Brackish groundwater is gaining increased attention as a viable resource. And in the case of Jordan, it is naturally occurring, but in other places, water resources or aquifers, I should say, are becoming brackish as a result of changed conditions, such as pumping-induced seawater intrusion, even pollution and climate change. Next slide. And the government of Jordan is now exploring options to enhance or develop new sources of water supply, given a very large gap between supply and demand and projections, with that gap just growing. And they have currently undertaking a very large, or planning for a very large design, build, operate initiative in the Gulf of Aqaba for desalination of seawater. But in the meantime, that has a long time frame. So in the meantime, they are looking at other options. And the German Technical Development Agency has supported the Ministry of Water and Irrigation and the Water Authority of Jordan with a project called Desalination of Sea and Brackish Water, which is what we worked under. Next slide. And brackish water is already used in Jordan. There's about 20 existing desalination plants that are used for public water supply, all really taking water from groundwater, I should say. All are based on reverse osmosis technology, and most of the plants are small. There's only really one big plant shown on the left there, with a design yield of more than 5,000 cubic meters per hour, and a design TDS, total dissolved solids, of 1.5 grams per liter. And that's actually a mixed groundwater, surface water sourced desalination plant. The production throughout these 20 existing supplies are affected by common problems associated with the well installations, insufficient O&M of plants, and some questions arising around the resource itself, so lack of resource characterization and monitoring. Next. So our study really was focused on trying to describe, put together, assemble, collate information to indicate the potential quantities that can be exploited, to identify where this water can be accessed, and to look at water quality information in context of the infrastructure needs that will be required to develop this water, and to dispose of this water, to develop initial cost estimate and look at risks of development. And importantly, identify data and knowledge gaps to sort of steer the way forward. And depending on where you are in Jordan, water can be difficult to access, or it can be very easy to access, as indicated by these two very different photographs. One in the desert area in the east, and the picture on the lower picture is from an existing production well right on the Jordan Valley. Next slide. And the information that we have about brackish aquifers, or brackish groundwater in Jordan, is largely derived from exploration well drilling in the past. Very importantly, and touching on the topic that John was talking about in Kimbiji, geological interpretations from the oil and gas sector. There have also been past modeling studies to kind of pull this together and look at potential flow fields and flow mechanisms. And really the main interest is in deep sandstone aquifers with exploration depth, depending on where you are in Jordan, from 200 to more than 1 kilometer. Next slide. So this slide here, this image is a geological cross-section in northern Jordan from west on the left to east on the right. So basically from the Jordan Valley / Dead Sea on the left to the border with Iraq on the right. And the target aquifer is the pale green on the bottom and the pale brown right above it, or the pale brown right above it. And depending on where you are in Jordan, these can be very, very deep, but in other parts of Jordan, they are very shallow and even outcropping. And flow in this case, groundwater flow in this case, is from the east to the west towards the Jordan Valley. Next slide. And this is just a plan view to show the flow field indicated by the arrows. The blue are where we have relatively good information on flow fields. The green arrows where flow is inferred. And the water is heading to the natural sink or the discharge area, which is the Dead Sea and Jordan Valley in the north. And but I mentioned that some of these aquifers are actually outcropping, and they are doing so in the south of Jordan. And the government of Jordan has already begun large-scale development now in the south, the DC project, where through dozens of production wells, they are now sending about 100 million cubic meters a year to Amman and north through a separate design build operate project. Next slide. And that means with large-scale development in the south, the major opportunities are in the north, and this is just where the study is recommending going for development along the Jordan Valley, but also on a structural high in the sort of central north part of Jordan. They're indicated by the thick red line box in the middle. That's a structurally accessible location to get to this water. Next slide. But water quality characteristics is a central theme because it defines the level of treatment that might be needed. And the water is aggressive. It's causing both corrosion and scaling, precipitation of minerals on existing infrastructure. The TDS that we see, depending on location, is anywhere from 3 to 10 grams per liter. The water has elevated iron, manganese, and sulfate. Again, that's location specific. There are turbidity issues, but that's not a natural water quality issue. That's related to well construction practices. But the water has, again, depending on location and where you are in the flow field, regional flow field, some natural radioactivity, and the same with temperature. Temperature is reaching 40 degrees plus centigrade. Next slide. And this is just an image of the corrosion and the, frankly, the rusting that you see on inappropriate well construction materials. Next slide. This is an image looking downhole. It's a camera image looking downhole in an existing production well. On the left in the dark area there, that is basically casing that is completely corroded out and is part of the issue with the turbidity that I mentioned. And the white area on the right is scaling, large scale scaling on the inside of casing, clogging up screens, etc. Next slide. So in conclusion, the good news is that there is brackish water available for exploitation, up to about 5,700 cubic meters per hour is a conservative estimate. The volumes are large, the aquifer system is large, and so we're not really worried about the time aspect of pumping that water. So we can demonstrate that brackish groundwater exploitation is practical. Water can be accessed, but it's not straightforward. There's still a significant characterization work to define, to describe, to understand how this regional system works. The water quality, definitely affects the selection of installation materials, and depending on where you are, it's really coming down to PVC or stainless steel. Pre-treatment is going to be a requirement, is required. And a very important topic that a colleague of mine will describe a little later today the brine discharge options may be limited because of the environmental effects associated with that. The brine is very concentrated, of course, and it has to be disposed of safely and in an environmentally sound way. And there are issues around sustainability, which has to be looked at further. Leakage between aquifer units when you start pumping regionally. One aquifer, you can impact on another. Well spacing and well field development is subject to good design so as to minimize well field interferences. And we still need to learn about potential water quality changes over time, how the hydraulics might still affect the water produced in the longer term. And I'll conclude with that. So thank you very much for your attention, and I'll take any questions you may have.
Thanks, Henning. Question to you. Is the water fossil or otherwise non-renewable water?
Yeah, so depends on where you are. No, the answer is no, it's not fossil. The aquifers, the sandstone aquifers that I'm referring to do actually outcrop, and they receive a very limited amount of recharge. So in the context of current recharge and current exploitation in the DC area, and in context of just the scale of this, I mean, somebody could argue, yeah, it's fossil, we're going to mine this water. But technically it is replenishable, and it is hydraulically connected to shallower units, primarily carbonate units, and there's interaction there too. So it's not a closed fossil aquifer in the sense that I think the question is being posed. Thank you.
Thanks, Henning. Okay, moving from the very dry country of Jordan to the very wet country of Ireland. I'm going to turn it over to our colleague, Philip Schuler, please.
Thanks very much, Jeff. It's my pleasure to present to you the methods and the results about quantifying the susceptibility of groundwater to drought across the Republic of Ireland, for which we used machine learning techniques as well as time series analysis. And I would like to acknowledge at the beginning the contributions from our client and partners from the Geological Survey of Ireland, as well as from CDM staff. Not only based on the 6th assessment report of the recent run of IPCC, we're aware of that many parts of the country, of the world, are facing increases in drought frequencies and magnitudes, which are projected to increase according to different specific warming levels, of course, and considering uncertainties in the models. Across Ireland, we also see that climate projections suggest increased number of dry periods in average per year, as well as most significantly during summer. Depending on the RCP, the increase of dry periods could reach 32 or plus 32 or 47% for the future period in parts of the country, but generally increased dry periods. Overall, one must bear in mind, of course, that droughts are not a new phenomenon in Ireland. We have to acknowledge this. They have appeared frequently over the last 200 years. Nevertheless, over the recent years, we have seen dry summers, most significantly, perhaps so far, the drought in 2018, which implied or which had impacts on ecosystems, agriculture, as well as water supplies. The 2018 drought was unprecedented for the national water utility, Irish Water. Water availability was heavily reduced in many parts of the countries. And from this experience, Irish Water learned that the existing assets are not as resilient as they really should be for these periods. And in consequence, the 2021 framework plan for the next 20 years acknowledges the impact of droughts very specifically by, for example, including a drought management in this plan. So the results of the recent climate projections and observed climate increased the determination to better understand how spatially drought may impact on groundwater resources. And as a result of that, we as CDM Smith were tasked to support the Geological Survey of Ireland in its effort to improving this understanding for climate change adaptation, for example. To do this and to answer this question that you see here on the slide, how meteorological drought affect groundwater resources, we start a few steps back at the conceptual understanding. What is groundwater? It's water underneath, and it often has what's called a groundwater table that you see on the left-hand slide. And this groundwater table fluctuates in time depending on rainfall input, but also depending on surface and subsurface properties, which filter the rainfall signal towards the saturated zone underneath that you see here in shaded blue. Depending on the surface and subsurface properties, groundwater levels fluctuate in time. On the top of this graph, you see a very flashy hydrographs. On the bottom, you see a more slower responding hydrographs. And these hydrographs, in essence, do not necessarily reflect the rainfall dynamics or the rainfall characteristics, but rather the surface and subsurface properties and how they affect groundwater levels. And our goal was in this work to use this information of time series, the characteristics of the dynamics happening underneath, to develop a map, a national map that quantifies the potential susceptibility of these sites of the subsurface to meteorological drought. And the results have been just published in the Journal of Hydrology, and there's a link given here at the platform. One quick overview in terms of methods that you get an idea very quickly. On the top hand, we see a map of Ireland. We used 114 groundwater level observations, many years of time series. We applied the autocorrelation function to quantify the linearity or the dependency within the time series. Here you see the arrow on the top, for example. A low slope means we have high linearity and low drought susceptibility, and vice versa. And then we applied a sliding window of the autocorrelation function on every time series. And on the next figure here, you see the probability density plot for all the quantified linearities, or what we call groundwater memory, across Ireland. So the groundwater memory then expresses how fast or how slow groundwater levels respond according to the properties of the surface and the subsurface. On the bottom, we see here our approach, how we applied a machine learning algorithm. As input, we used our groundwater memory that we quantified, as well as national thematic maps, such as the depth to bedrock, the subsoil permeability, the absolute, the relative topography, etc. And this data we combined to apply, use a random forest regressor that we built in Python, or we applied it in Python. The model was, of course, trained. It was validated using independent data. And along with QGIS, we then inferred or modeled the susceptibility of drought across the entire country that you see here on the last image in blue and yellow color shadings. On the next slide, you see the high, moderate, and low groundwater drought susceptibility from left to right. High susceptibility on the left-hand side, we have in areas where we have high relative and absolute topography, elevations, and minor overburden thicknesses, mostly in the western part of the country, as well as in the eastern part. Low susceptibility, on the other hand, in the blue shaded colors, we have in areas of low topographic elevations and thick overburden that acts as a protection layer, mostly in the center of the country. And to conclude, the drought susceptibility displays areas where groundwater is expected to be more or less affected by meteorological drought. It is independent of the rainfall signal, really, but it is only based on the surface and subsurface properties. It's important to notice. We expect that it's used for water management. That's the purpose of the study. It has implications for users, no matter if it's a domestic supply or agricultural supply. And in our understanding, it is very important for climate change adaptation in the water sector, because, as I said, you see areas where we expect groundwater to be more or less affected by droughts. The good thing about this method, we believe, is that the method can be applied anywhere in the world, really, where there is groundwater level observations, where there is time series of sufficient length, of course, as well as where there is thematic maps. That's a matter of scale. It's a matter of course, retraining, re-evaluating a model. There's no guarantee that a model will work, but in principle, this approach can be applied anywhere in the world. And yeah, thank you very much for attending, and I look forward to answering any questions if you have.
Thank you, Philip. Checking questions here. So, Philip, as I understand, the topography and overburden thickness controls the groundwater susceptibility. Were there any additional variables that influence the susceptibility? And overall, were you surprised by the results, or do they rather confirm your expectations?
So, yeah, firstly, yes, it's correct. It's overburden thickness and the elevation. We use the absolute elevation of a digital elevation model, as well as elevations, what's called from a hand grid, height above nearest drainage. Yeah, I was surprised that the topography played such a big role. I mean, it was really these three variables: overburden thickness, hand, and digital elevation model, that controlled it. I was surprised that it's only these three most significantly. I mean, it makes sense from a conceptual point of view. I mean, for example, Henning, he worked a lot in source pathway receptor analysis, and there is this conceptual thinking of pathways, how they concentrate towards a receptor following the topography, more or less in some instances. And I guess that's kind of like what also comes out of this, because yeah, we see that topography guides the way how fleshy, how responsive the hydrographs are. So in lower elevated areas, we have flow concentrating towards these areas. So the variations of groundwater levels are not as much as in higher elevated areas. So yeah, it does make sense. Yeah, I hope I could answer the question.
Yeah, that's great. Thanks, Philip. Okay, so let's move to the Q&A discussion. So at this point, before we move on to the second part of our presentation, we'll open it up to questions about any of the three presentations that have just been shared. So please drop your question in the polls, not the chat. And again, this is on the World Water Week website. And include your email address again, so we can follow up if we don't get to them on air. So I'm going to hold for a minute here and see what questions come in. Takes a minute to refresh here, so let's give this one more second before we move on. All right, well, it doesn't look like we have any poll questions coming in, so we will offer a second Q&A session after the end of part 2. So let's move to that. And in part 2, we're going to start off with a discussion on groundwater desalination in the US by Greg Wetterell. Greg?
Thanks, Jeff. So yes, go to the next slide here. So when we look at adapting alternative water supplies, desalination technologies provide a lot of different opportunities for water stressed locations to get new supplies of water. And today there are over 94 million cubic meters per day of installed desalination capacity worldwide. The figure that's shown here came directly from an AWWA manual that I worked on for inland desalination. Is M69, but the original data source came from a partnership between IDA and Global Water Intelligence, and they track these statistics from year to year. But if you look at this graph, over 70% of the desalination installed today is treating either seawater or tidally influenced rivers. So the vast majority of these plants are located in coastal areas where low-cost brine disposal alternatives are available. And for that reason, brine reduction has historically not been a major focus of desalination plant design. So the next slide. So understanding the issue of brine generation with desalination, this figure gives you a simple schematic of a reverse osmosis system. So a seawater plant typically runs with a single RO stage, and it operates between 45 and 60% recovery. So this means that for every cubic meter of water drawn into the plant, around half becomes product water and the other half becomes concentrate that needs to be disposed of. Now for a brackish water plant, we typically add a second stage, so taking the concentrate from the first stage and running it through a second stage. And this allows the plant to increase recovery to between 70 and 85%. Now, in some cases, depending on water quality, a third stage can be added, and this will take the recovery to between 85 and 94%. So with a traditional RO system running at the highest recovery possible, you could have a waste stream that's as low as 6% of the influent flow, and it's going to contain nearly all the salt of the feed water, or a 16-fold increase from the source water. So if you started with 2 grams per liter TDS groundwater, your brine stream is going to have 32 grams per liter, or something similar to ocean water salinity. So driving the recovery higher reduces the volume you need to dispose of, but it also creates new challenges for disposal options. Next slide. So I mentioned that globally, the majority of desalination plants are treating seawater, but in the United States, it's the opposite. We have over 90% of our municipal desalination plants treating brackish groundwater. We have over 400 municipal plants producing more than 8.3 million cubic meters per day. And nearly 80% of these plants are located in states that border the ocean. And this provides them lower cost alternatives. But you can see from the map here that we do have a lot of desalination plants in landlocked locations. We have 10 in Colorado, 16 in Iowa, 12 in Illinois. And with more plants moving inland and larger plants being built, brine reduction is becoming a major focus in the United States. Next slide. So if you look at the existing concentrate disposal approaches used in the US, around 75% of the existing plants have a surface water discharge or a sewer connection for their concentrate disposal. And these are plants that are either in coastal areas or they're small capacity, small enough with limited impact on the environment to allow for this kind of a discharge. Now, for plants that don't have that option, around 17% of them have a subsurface or deep injection well where a concentrate is injected into a confined aquifer that's got to be hydraulically disconnected from drinking water supplies. And then only around 4% of the plants have evaporation ponds, and less than 2% are operating with zero liquid discharge. So, okay, next slide. The type of concentrate disposal is going to vary by geography. So here I'm in California, and in California and Texas, over 90% of our plants have surface water or sewer discharge, but the arid environment in these states does allow for evaporation as an option. CDM has put in 3 plants here in California with evaporation ponds, but the state only has 1 deep injection well, and that's due to seismic activity, making it difficult to find reliable confined aquifers for disposal here. In Texas, in contrast, there are a couple different projects with deep injection wells. One of them we did in El Paso, and there are a number of plants with evaporation ponds as well. Looking in Florida, in contrast, around 17% of the plants there have subsurface, or around 36%. 36% of the plants there have deep injection wells for disposal. And the state really has a very good, well-confined, highly permeable brackish aquifer that allows them to use deep injection wells for disposal. Nearly all the plants, or all but one of the plants that I've worked with in Florida over the last 23 years, has used deep injection wells for their disposal options. All right, next slide. So for facilities located in inland location, brine reduction options are needed to address environmental concerns and to keep the plant affordable. As I mentioned earlier, a conventional RO plant is generally not going to be able to achieve recoveries above 80 or 90%. So to get to higher recoveries, there are proprietary processes available to take recoveries up to 96 or 98% using RO. So these are things like closed circuit desalination, the HERO process, the OPUS process, but a lot of them, there are also non-proprietary approaches using chemical softening tied with RO to get to these higher recoveries. But once you get to that point, getting that last 2 to 5% out is going to require either evaporation or a crystallization process. And these are very, very costly. And it's a huge driver to try to increase the recovery on the upstream processes. So just looking at costs on the next slide, the cost of developing a brackish desal plant with a typical, assuming a typical recovery around 80% without brine disposal cost, it's going to be on the order of $200 to $300 per cubic meter per day capacity. And again, this is just construction costs. So if you need to use deep well injection for disposal, it's going to add between $200 and $1,000 per cubic meter per day to the cost of the plant. So it's essentially doubling the cost of your system. If you can't use deep injection wells, the cost of evaporation ponds would add $2,600 to $5,300 per cubic meter per day of plant production capacity. So this is a 10-fold increase in the cost of the plant. If you want to use crystallizers, they're a little bit less costly than evaporation ponds on a capital standpoint, but they have very high operating costs, and this could end up being more expensive from a life cycle basis. But because of the high cost of these brine disposal options, there's a large driver for increasing the recovery on the upstream RO system. For instance, if you can take the recovery from 80% to say 95%, it's going to decrease your brine disposal cost by 75%, making your overall project nearly 75% less costly. All right, next slide. So in summary then, increasing water stresses and technology advances are prompting more inland locations to consider desalination. Environmental considerations often prohibit surface discharges, resulting in an increased focus on brine management and beneficial reuse here in the United States. Advancements in brine reduction technologies have been reducing the cost of inland concentrate disposal. And as technologies mature and innovations continue, I expect the use of inland desalination to continue to grow, allowing greater use of untapped water supplies, both here in the US and throughout the rest of the world. Thanks.
Thanks, Greg. What are the key issues that are preventing brackish water desalination from being used more outside of the United States?
Yeah, I mean, I think the main issue is really just this brine disposal question. If you're in a coastal area, you do have a relatively low cost option, but a lot of the water stressed areas aren't that close to the ocean. And so that's been, it continues to be a big concern, but I think a lot of it is just a lot of the water utilities and water supply planners haven't really considered this as a viable option, and they haven't seen how well it's been adapted in a lot of different places. So I do think that as more information gets out there and more places start putting in brackish desal, you're going to continue to see it grow more and more, because I think a lot of the key issues have been worked out. I think we do have a lot of options for brine disposal, but in some locations, just depending on where you are, it could be more of a challenge than for other places.
Okay, great, thank you. Okay, moving on from California to Santiago, Chile. Jose Maria Guzman is going to talk about seawater desalination in the mining industry. Over to you, Jose Maria.
Thank you, Jeff. Thank you very much. Indeed, my name is Jose Maria Guzman. I'm a water resources engineer here at TD & Smith. I'm Chile country manager. And today I want to talk to you about this specific case of finding a solution for a water stress situation in Chile. My next slide, Jen. I'd like to give you an overview of what Chile is facing these days. Chile is a country that you might know in South America with a very long coastline. It's 4,500 kilometers. That's as much as the border between the US and Canada, all of coastline. And most of the users are located within a short distance, up to 150 kilometers. The only drawback is that some of the users are actually at high altitude in the Andes Mountains, but relatively close access to the ocean coastline. And the country is going through an unprecedented drought. If you look at the records, they have had never so many consecutive years of drought in this part of the country. And that's generating a problem for freshwater sources. And in some areas, even without the drought, that they were already stressed. And in addition to the drought condition, the country has been looking at making major changes to the way it manages water. This is one of the only countries in the world where the water is privatized, and there have been efforts to improve the way it has been managed by making changes to the water rights, and most recently with constitutional changes that are going to be vetted in 2022, in which the change is going to give now priority access to the community instead of private use. And that is also giving an additional challenge to private users like the mining industry. Chile, as you might know, has a significant mining industry for many metals such as copper, iron, lithium, molybdenum. And the mining industry is looking at ways to cope with this drought and these changes in water rights. What you see here in the picture is one of the seawater desalination plants that was built near Mejillones in the north of Chile to deal with this situation. So let's talk a little bit more about seawater in the next slide and how seawater is really becoming part of the solution for the mining industry. Because of all the conditions I mentioned earlier, basically the mining industry is looking at how to implement seawater as a source for its operations. And what you see here is data from Cochilco, it's a state agency that oversees mining companies in Chile. And you can see the historic and projected data on how the fresh water that you can see here from the year 2020 to 2032 is going to reduce in demand from 11.2 cubic meters per second to 5.9. And that is compensated by an increase in the use of seawater, mostly desalinated seawater, but it's also use of seawater without any particular desalination process for some of the mining industry. So as you can see, a significant increase is expected up until the year 2032. And in the next slide, what I wanted to give you an overview is that how intense is this initiative really happening in the north of Chile. What you see here in the map, as you can see in the location map, we're looking at the northern part of Chile, an area known also as the Atacama Desert, one of the driest parts of the world. And that's even before the drought. So definitely an area that is challenged for water availability. And in the year 2021, as you can see, there are so many ongoing projects shown in this map. The ones in the left in blue are projects that are already in operation. And you can see that there are two of them with the yellow star, which indicate they are public utilities, but all the other ones are already mining-related desalination water plants. And on the right, you see the ones that are in the project or study phase. Some of them are in permitting, some others in design, some others getting close to construction. And you can see the different capacity of these plants in design flow. They range from 300 liters per second to more than 3,000 liters per second. And CD Smith is supporting many of the mining clients to help them understand the challenges, the design issues, and the operational issues associated with desalination plants. So in the next slide, what I wanted to mention to you is that this amount of activity and this initiative from the mining industry is allowing Chile to develop environmental standards, because seawater salination has some precedent in some countries like the United States, Australia, and Spain, and I would say mostly in the Middle East as well. And these countries have developed standards for some of the permitting that Chile has been incorporating in its own processes, particularly when it comes to some of the features of these plants. The seawater intake design, because most of these plants, because of their size, they don't rely on beach wells, but actually they have open intakes in the ocean. They have to be designed properly. So and they are designed in a way that there is safety to any nearby swimmer, to all the fish, to all biology around the area, the currents, and all of those criteria are being considered in the design. What you see in the picture here of the quadrant, it's one of the surveys that look at the diversity on the biology around some of the intake and outflow structures of the desalination plants. And then following the trend of my previous two speakers, brine disposal is a significant issue, more than anything because it's important to gather field data and confirm that the designs that have been used are not harmful to the environment. And what you see on the right here is one of the diffusers of one of the plants from Aguas de Antofagasta in the north of Chile, in which the design is meant to really diffuse the high salinity of the brine within a short distance to limit the area of influence. And there have been records showing that the reduction is achieved within a distance of less than 50 meters, allowing it to be really absorbed by the ocean. So that's additional information that is being gathered right now. And energy consumption. There have been significant improvements in the industry to reduce the energy requirements to desalinate seawater. And all of these are elements that are being taken into account by the Chile environmental standards. In addition to that, in my next slide, what the Chile industry has been doing is having a significant number of plants in operation, as you saw in the map. And that's giving an opportunity to develop operational standards dealing with water quality. You would think that the ocean water is there, it's available, that the quality is pretty stable, but the reality, it actually poses a significant challenge because you deal with changing conditions, jellyfish, red tides that change water quality significantly, and they happen more often than you would think. So your design and your operation needs to be prepared for dealing with this. The fact that there is need for preventive maintenance and corrosion associated with seawater that needs to be included in the design and the operational standards. And most of these projects, as I mentioned, have distance between the user and the plant, and that's covered by a pipeline that, of course, get exposed to corrosion. And that's why pipeline protection is so important as well. And a lot of data has been gathered and experienced, and CD Smith has been helping with operational consultancies, many of our clients in Chile. And with that, I'd like to basically summarize in my next slide, Jennifer, that the reality is that Chile is facing significant challenges related to the drought and the changes in the water rights that are hoping to improve the way we use water resources in Chile. And the mining strategy to reduce its impact on fresh water has included seawater desalination. That it's basically generating the projects that you saw in the presentation, a numerous number of projects in different locations. And that's allowing Chile to gather significant experience in both environmental permitting and operational standards. So hopefully that continue to be an area of development that can be used in Chile and elsewhere in the world. And the thing is, now with the changes that are happening at the constitutional level, we hope that water reuse is also going to be much more a accessible, and being also a competitive solution to work along with desalination and other methodologies to cope with the water scarcity that is happening right now in Chile. So with that, Jeff, thank you very much for letting us talk about this Chile case, and I'm open to any questions that you might have.
Thanks, Jose Maria. You mentioned that there has been an emphasis on energy costs and efficiency. What is the current cost of seawater desalination in Chile?
That is an interesting question, because it's cost is not an easy summary number. You've seen the inflation, you've seen the difficulty in getting supplies, and all of that is having an impact on the actual cost. So maybe we can split the question in two. When it comes to cost, I would say that the cost, including construction, operation, financing, it's getting a little below the $0.50 per cubic meter. It's actually close, I would say, to 0.4, 0.45. But more than that, I would say that it's interesting to look at the actual consumption of energy, not the cost, because as I mentioned, the cost of electricity is changing so much everywhere in the world right now that it's difficult to make a comparison. And in terms of the cost of the power consumption, we are achieving 3.2, 3.3 kilowatt hour per cubic meter. And that's continuing to improve as we have better and better technologies to improve the efficiency of reverse osmosis for seawater desalination. So I would say those are the ranges, and it's a cost that is becoming lower and lower as we improve the technology.
Great, thank you. Okay. So now we'll open up to any questions for the two desalination presenters we just shared. Once again, for anybody who's new to join, please drop your questions in the polls part of the World Water Week website, and include your email address so we can follow up with you if necessary. Let me move over to the polls and see if we've got any questions for the desal folks. I'm waiting for some stuff to come in. Greg, question to you. What countries are you seeing outside the United States that are embracing brackish water desal?
Yeah, well, Jordan is the one that surprises me the most. Henning presented on that, but we've been working there for a few years now, quite a while. But the more I've been working there, the more I realized they've got a lot of plants. Now, most of them are small, but they have a lot scattered around. And so, I guess that's showing that even when, desalination has mostly been, at least for seawater plants, very strong economies, Gulf countries, and Australia has some of them. But brackish desal is a lot more affordable. And so if you have the right kind of supply and it's sustainable and you can do something with the concentrate, it does provide a lot of option for places that can't really afford the high cost of seawater desal. So yeah, again, I think North Africa, there've been more of these plants going in. You're starting to see them in the Middle East. Yeah, I think I haven't seen them as much in South America, Asia, but I think that we'll start to see a lot more of them as time goes on.
Great. Thank you.
Jeff,
Maria, yeah.
there are questions in the chat on the webpage.
Yep, I am seeing a question in the polls too. So, Jose Maria, question, can you explain more about how the disposal of brine is done in the ocean? You had mentioned a certain method of disposal.
Yes. The most common method that has been used for big capacity plants is to basically have a set of diffusers that are spaced at a certain distance, and we study basically the availability of the ocean currents to absorb the brine with different diffusers at different locations. And the diffuser has the objective of spreading the brine at a certain velocity that promotes basically its diffusion and its integration with the rest of the ocean water. So basically, you have an underwater pipe, usually at, I would say, 300 to 500 meters away from shore, at a depth, usually I would say greater than 20 meters depth. And then at that point, you have the number of diffusers, depending on the size of your plant, that, as I mentioned, are placed at an angle that is designed, again, in agreement with the ocean currents and with the velocity that promotes the dilution of the brine in the ocean water. And that's one of the pictures that I showed earlier in the presentation. Yeah.
Great. Thank you. Greg, I'll give this one to you. Are there any specific quality and environmental impact requirements or regulations in place for brine discharge specifically, or is this something that's been developing or is developing?
Yeah, and I'd say both. The answer is yes for both. It is developing, but there are regulations in place. I know, like here in the US, we've got regulations for wastewater discharges and industrial discharges, and we're trying to adapt them to the issues related to concentrate or brine disposal. And they don't always directly apply, like especially a lot of states here in the US, they don't have TDS limits on their discharges, even though they probably should, because it just hasn't been an issue in the past. And so they're, for regulators to approve these, they don't always have good regulations to base it on. They makes them a little bit nervous. They don't want to approve it at all in some cases, or in other cases, maybe they approve things they shouldn't. So I think they are developing, but there are existing regulations in place that are being used. And I think as more seawater plants go in around the world, a lot of countries are starting to develop their regulations more as well. And so they're definitely evolving.
Jose Maria, what are you seeing in Chile?
Yes, I agree with Greg. The fact that the US really hasn't developed that much of seawater industry, desalination, it's allowing other countries like Spain and Australia that have developed bigger plants to gather all that information and being used, as I mentioned, in environmental regulations. Chile is now developing a lot of that data as well. So as we learn more from these ongoing projects, I think we're going to keep improving the environmental regulations. The methods that I described earlier, for example, the diffusers, have proven to limit the area of influence of the salinity of the brine disposal. But of course, we need to keep looking at this and all these projects and all these data in Chile. And in the Middle East, there is a significant number of plants as well that can provide data. And that's going to allow us to keep improving the environmental regulations.
Excellent. Thank you. Greg, I think you answered this, but I'll ask the question again and then follow up with a why. So does inland brackish desalination require less energy than seawater desalination? And if so, why? Yeah,
it's about 1/10 of the energy. So it's a big deal. It's a huge savings there. And it's just because the salinity is a lot lower. I mean, if you're dealing with 1,000 or 2,000 milligram per liter source water, that just the osmotic pressure created by that it's just a fraction of what it would be for a seawater plant. So on an energy standpoint, much lower energy. Where that changes though is if you're inland and you have to go to zero liquid discharge, you have to concentrate up to 32 grams per liter. Some of these approaches, like evaporation ponds, they don't take much energy, but they're very expensive. If you go with a crystallizer or a mechanical evaporator, they're very high energy. And so now you're starting to get up to the energies that you would for a seawater plant.
Great, thanks, Greg. Jose Maria, another one for you. Have membrane technologies /RO been used in the mining industry in Chile?
Yes. they have been used before seawater salination. They were already used in some of the water treatment plants that are built specifically for some of the mining facilities. And then with the seawater desalination industry, in Chile in particular, it has always been focused around reverse osmosis, which uses membranes. So yes, they are part of the project that I mentioned, and they have different kinds of membranes that are being used. There's also new ideas about ceramic membranes and other types of membranes that will be used, but the mining industry has been definitely using them for quite a while now.
Okay, great. Another follow-up question to you, Jose Maria. Do you think there's an opportunity for open source data sharing based on the brine discharge impacts? As a follow-on to your comment regarding countries collecting data on this and how it can be used to improve and create regulations.
Yes. Well, for example, CDM Smith, we are members of some of the associations that are pushing for this, like ALADIR, which is the Latin American chapter of the IDA, the International Salination Association, and ACADES, which is the Chilean entity that also looks and oversees the industry that works with seawater desalination. And we're all pushing for that because the data is there. The current permits require to disclose environmental data associated with these discharges. And now it's the time to get all that data, as we are beginning to do, to be able to get it from the specific project and gather all this intelligence to really allow, hopefully, the universities and the academic community to help the industry review the data, agree on the potential impacts on how we can improve it. So the answer is yes, the data is there. The requirements on the permit is already enforced in Chile. And what we need now is to get that data out to the community that can use it. And this data is public. Anybody can go and get it, particularly in Chile, where the data is stored in the SEA, in the entity that oversees the permitting process. So anyone interested can look for the projects and get the data and start processing it and confirming what we're seeing on all the topics that I mentioned earlier.
You know, but that's a really important question, though, and I'm glad you asked that one, because it's historically been more of a challenge. A lot of these desalination plants are very proprietary. They're they're business ventures, and they consider their water quality to be intellectual property. And so they haven't always wanted to share this kind of stuff. And I think that is changing a lot more. And depending on what country you're in or where you're located, the regulations may require that to be publicly reported. I know in California, any discharge water quality has to be, this is regulated and it has to be reported. You can look it up on the web for anyone. But certainly what Jose Maria was talking about with these professional societies pushing more data sharing, it's going to really help the industry in the long run.
Agree. Totally agree. Yes.
All right. Give it just a few more seconds here. Let's see if anybody else has any last minute questions. And it can be to all of our speakers. We don't have to just focus on the desal, although that seems to be the hot topic right here for our questions.
That's what happens when you're the last speaker.
The last speaker before lunch in this time zone. Okay, one more check here on the refresh button. All right, that looks like it for Q&A. Jen, let's wrap this up. Let's go to the conclusions, please. Thank you. So, from drinking water to agriculture to industry, we rely on these groundwater resources. Increased extraction combined with climate change will decrease the quantity and quality of them. Thus, new tools and techniques will be required to prepare for this future. We hope that the information we shared with you today and the takeaways captured in this slide generate new ideas about how you can address the climate change-induced groundwater challenges you may be facing. We'll be leaving you with a list of works cited in the next couple of slides, which will also be available in the file selection of the Pathable platform. So thank you for your attention today and have a good rest of your day.
Thank you, everyone.
Thank you.
Thank you.